Hey, welcome to Mineral Talks Live, the weekly live webinar that brings you in-depth and in-person interviews with the mineral people from around the world. Mineral Talks Live is brought to you by a joint effort among the Mineralogical and Geological Museum at Harvard University, the Society of Mineral Museum Professionals, and Blue Cap Productions. Tune in every Wednesday and stay connected to your mineral world. Now, broadcasting live from beautiful Honolulu, Hawaii, the land of aloha, ukuleles, and shakas, this is Mineral Talks Live. Hello everyone, thank you for joining us today. In case you haven't been keeping track, today is Wednesday, May 26th, 2021, and that makes this the last Wednesday of the month of May. Now, this weekend is Memorial Day weekend, which here in America marks the official start of summer. So slap on that sunscreen, grab your surfboard, and hele on down to the beach. You're watching Mineral Talks Live, and we're thrilled that you could join us here today. I'm Brian Swoboda, the president of Blue Cap Productions, and together with my phenomenal partners, Dr. Raquel Alonso Perez from the Mineralogical and Geological Museum at Harvard University, and Dr. Eloise Gaillou from the Society of Mineral Museum Professionals, also known as the SMMP, we want to welcome you to the show. Our goal in producing this program has always been to focus on bringing together all the different facets of our mineral world, from curatrix and curators to collectors, dealers, miners, researchers, artists, and the media that serves us all. We hope that in doing so, we show our audience how diverse our little mineral world really is. We invite you to participate throughout this live show, either through the chat feature or the Q&A feature, both of which are located at the bottom of your Zoom window. The chat feature allows you to type messages to everyone watching the live show, and as we're all about community, when you first sign on, go ahead and fire off a hello to everyone telling us where you're from. Also, if you have thoughts or comments during the show, this is where you can post them and interact with each other. Now, during the interview, my guest and I may not see all your chat messages, but both Raquel and Eloise will be very active in those chats, so look for their comments and links. When appropriate, either Raquel or Eloise may address us directly with some of your questions. The second way to interact is with the Q&A function. This allows you to submit general questions that we'll try our best to answer at the end of the interview. Finally, at about 40 minutes into the program, you'll see a window pop up on the screen asking a bunch of questions for our Quick Fire 5 segment. This is where we get to see how well you know our guest. It's always fun and sometimes a little bit odd, but come on, play along. Now, for today's show, we're headed over to Washington, D.C. to catch up with a man who needs very little introduction, Dr. Robert Hazen. I first met Bob back in 2014 when he gave his presentation on the Great Oxidation event at the Dallas Symposium. I was completely blown away. He presented some concept that really showed me how integrated minerals are to life on Earth. Since then, I've seen more of his presentations and learned more about what he's done, and my respect for him has grown and grown. So it's my absolute honor to have Bob on the show with us today. Hi, Bob. Thank you for joining us, and welcome to Mineral Talks Live.
Ryan, hi, and hello, everybody. Great to be here.
How you doing out there? We were talking earlier, and the cicadas are out in bloom right now, correct?
Phenomenal. It's miraculous. This explosion of these beautiful insects and how they go through their 17-year life cycle, and they just come out of the ground and crawl up the trees, and now they're making a racket outside. It's really a wonderful natural phenomenon.
Well, hopefully at the end of the show, if we have time, you might be able to crack a window or take us outside and we can hear them for ourselves. Hey, Bob, on this show, I always like to turn back the clock a little bit and talk about what got people first involved in minerals. And so you are more on the mineral research side, but the same question applies. What kind of first got you interested in minerals and mineral research? Was there a particular moment where it was like that Damascus experience, that aha moment where you said, this is it?
You know, Brian, right from the youngest age, 5, 6, 7, I always liked to collect things and study them. I lived at that time in Cleveland, Ohio, and our backyard bordered on a very swampy area. So I collected butterflies and moths and insects. And Cleveland, that area is very fossiliferous. So we'd go on the weekends to Rocky River Park. It was a park that sort of surrounded the city, and and we pick up stones and skip them. And I remember I actually have, I think I collected this when I was about 6 years old. It's a specimen that I didn't want to skip. It has these little tiny fossils called tentaculites on them, little narrow conical ridged animals. I'm not even sure what kind of thing they are, but I picked that up and began collecting fossils whenever I could and go on weekends to quarries and places like that. So after my third grade, we moved to northern New Jersey. And northern New Jersey is not a fossiliferous rich place, but as all of the viewers here know, it's unbelievable for its minerals. And so my allegiance switched from fossils to minerals, and I'd go out on weekends and I'd go collecting and I'd try to find things. And I sent you a photograph, a set of photographs of one of the very first specimens I found in Paterson, New Jersey. It was the road cut. And so
let me go ahead and pull the photograph.
Show people that, because this is something just fascinating. This is a micro amount. These are 1 millimeter across crystals, and if you look closely at this, especially in the next slide, you'll see that there's kind of a fascinating phenomenon going on here. Alternate faces are coated, and I saw this and I said, well, it looks like quartz has six-fold symmetry. It looks hexagonal, and yet only opposite faces, alternate faces are coated. Why would that be? And it's just something that bugged me, and I was curious about it. I want to learn more about it. As I went on through my career, it was many years later that we started understanding in detail the atomic structures at the surface of these minerals. So if you look at the next slide, you'll see here's this visualization of a quartz surface, and you'll notice that those terminal faces have different structures. And so what you see in the next slide is that hematite doesn't want to, it sticks to this face because the arrangement of oxygen atoms at the surface is the same as that of hematite. But if you look at the other face, the 011 face, the arrangement of oxygen atoms aren't the same. So hematite only grows on alternate faces. And that was the kind of question that just totally fascinated me. And a little bit later, maybe we'll ask everyone watching today a little mystery we have, because I found another specimen at Tucson a couple of years ago, and I still don't know where it's from or exactly what it is, but it has the same phenomenon in a macroscopic specimen. And
that'll be our Stump the Viewers segment.
Stump the Viewers. We're going to.
Everybody has Mindad.
The
They're bringing up Mindad on their computer right now.
Yeah, I know that somebody knows this. And then. I also, we were only an hour's drive away from Franklin, New Jersey, and it was incredible. My father was an electrical engineer. So back in 1964, 65, we designed and built a portable black light before they were commercially available. And so this has a NiCad battery in it. It has a Corning UV filter. It has a germicidal bulb, and we could go out, and this had about a 2-hour lifetime. So we'd go out to the buckwheat dump in the mid 60s before a lot of people were collecting, and just we had the most incredible fluorescent rock collection. In fact, we'd bring back boulders. We'd bring back things that weighed more than 100 pounds, and we had a fluorescent rock garden in our New Jersey yard. So I remember distinctly, we had a 55 Buick at the time, and we'd load the trunk up so full with rocks that the suspension, it would be like we had our brights on, and all the cars that passed us on these back roads in Sussex County, New Jersey, would flash their lights. Oh, you're shiny, you got your brights on. And it isn't. It's just that we had a trunk full of rocks. And the kinds of things that fascinated me, this doesn't look like much. This is a Franklin chunk, but it's to me, this is an amazing specimen, because one side has the typical red and green fluorescence of calcite and willemite. The other face has just willemite, bright green when it fluoresces, but it's only this face that has the persistent luminescence, what we used to call phosphorescence. And I always wondered, well, why is willemite here phosphorescent and why is the willemite here not? That's the kind of question that just interested me. So it was only a couple of weeks ago that I learned the answer to that from George Harlow in the new American Museum exhibit. That it's just fantastic. It opens on June 12th, and it has to do with primary versus secondary willemite. But those are the questions that just kept intriguing me. And every time I found a new mineral specimen, there were more questions. And so I just kept studying, and I I don't know when I'm actually going to grow up and decide what I want to do for a living. But until I figure that out, I'm just going to, have fun with minerals. That's what I like to do.
I absolutely love it. You have this childlike exuberance about it. And we sometimes are jokingly critical of children because they always ask why. But I submit that is a incredibly useful tool for understanding the world around us. And you were that same way, it sounds like. You kept asking why, and you are continually asking why.
And I was incredibly lucky, Brian, because I had teachers that didn't beat out that curiosity, but rather encouraged it. And most important was my 8th grade science teacher, William Welsh. Okay. Welshite was named after him. He was the president of the North Bergen Mineral Club. He traveled around the world. And when I was in 8th grade, he gave me a collection of minerals and gave me mimeographed sheets of, Patterson and Ringwood and Franklin and other places that were within a easy drive, and just really nurtured and said, you can learn this, you can do this. And then, son of a gun, I went on and I found I could actually, quote, do this for a living, which just seemed like a racket to me. Wow, I didn't have to work. I could do mineralogy.
If I can do this and make a living, well, I've found the secret of the universe. Well, it also sounds like your father was very involved and very encouraging in what you were doing and participating with you, which makes a huge difference.
Oh, absolutely. My parents were so encouraging, and they recognized that I had an interest and a passion for these sorts of things. And, I would go into the American Museum of Natural History on a monthly basis for years. I'd go in and spend time in the Morgan Mineral Hall and look at the Dana collection and study case after case after case and systematically go through it. So I just had great opportunities. I had great teachers. And I do think it's important for us to recognize that the opportunities that I had were not available to entire groups of people. In those days, women weren't encouraged the way they are today. And certainly there were virtually no minorities in the field. And I want to just take an aside and recognize that I've been incredibly lucky. And I've had advantages that many other people wouldn't have. And that's something that I now take incredibly seriously, that it's an obligation to the next generation to make sure that the equities are brought forth and that the inequities of the past are reduced.
Oh, wow. I couldn't agree with you more, Bob. In our interview with Elizabeth Rampey from NASA, we touched on that a little bit, where she is a strong proponent of gender and cultural equality, recognizing the advantages that she's had, and she's trying to pass that on. So hats off to you for doing that as well.
Well, it's something we can all really take to heart.
Absolutely. Now, Bob, I imagine that the encouragement that you've gotten from your father has been passed on, and you've got a beautiful photograph of your grandson on the cabinet behind you. What have you done to kind of pass that on to him?
Well, Greg has so many interests, and my gosh, so we take him out collecting. We've gone mineral collecting and fossil collecting, but he also has found his own path. He's an incredible musician. Really incredible computer programmer, and he's learning coding and that sort of thing. So I don't know what he's going to end up being his ultimate passion, but he's found many things that excites him, and we just encourage him and hope that he finds a path that's fulfilling for him as mineralogy has been for me.
Wow. So he is a mineral collector, he's a musician, and he's into computers. Sounds a lot like you.
Well, I have to say he's not as much of a collector as I am. And I think that's sort of something that's also very emblematic of kids these days. I've seen many of them are not as material. They don't surround themselves with lots of stuff. They don't, look at my shelves. I've got tons of books. I've got records. and everything for them is sort of an electronic medium. And that's what he's doing. He's doing electronic composing, and he's writing codes. And so I think that his interests have this more abstract quality in that sense, but I think they'll take him a long way.
Oh, absolutely. I think that's the future where the world is headed. There's no staying away from it, and I don't think there needs to be. But yeah, that's great. So, as a teacher, what are you and your students working on right now?
Well, it's interesting you say me and my students, and I just can't think of the colleagues I work with that way. I have early career colleagues, and every one of them knows so much more about many things than I do. So I hope they learn some things from me, but I learn so much from them. So this is a mutual learning environment. And what we're thinking about primarily these days has to do with bringing mineralogy into the era of big data. Now, there are pioneers, there are incredible people. You had Jolyon Ralph on. He is a hero to me. Bob Downs and the Rough database, Kirsten Leonard and EarthChem. These are people who are making fundamental contributions to the field. But the future of mineralogy has to be to build larger and larger and larger data resources and then to analyze them in new ways. And so that's really what we're figuring out new analytical and visualization methods in mineralogy. I mean, the things you can do when you have large data resources, just one example, something called association analysis. You know, when you buy a book on Amazon or you get a video from Netflix, they'll immediately come up with recommendation for something. Oh, if you like this, then you're going to like that. And the algorithms, the computer algorithms to come up with those recommendations are not trivial because they're recognizing things you like, things you don't like, things that other people like and don't like. And it's a very complex, higher dimensional problem to recommend to you the next thing that you might want to buy or to view. Well, you can do the exact same analysis with minerals. What mineral is likely to like to be with or not with other groups of minerals? Say you want to find another occurrence of gillespite. And there are ways using these mathematical algorithms to make predictions. If we go to this locality based on MinDat and all of the minerals that occur at certain localities that are known, and all the minerals that don't occur at those localities, then we can say, here's the high probability, and you give it actually percentage probability of finding new minerals. And we've actually begun the process. Jolyon has predicted the locality of a wolfenite crystal, I believe it was in Utah, and sent collectors out there, and they found wolfenite where it had never been reported before. So, wow. And this is now being used by mining companies to expand not just to wolfenite, but to lead deposits or to copper deposits or other sorts of resource development. It's an incredible frontier, but you need huge data resources to do it. And so that's one of the many directions that we're exploring. I'm so excited about this. So working with my colleagues now, this is kind of a frontier for us.
I love it. What a great example. Now, I think back to the example of benitoite, and the crystal structure of benitoite was discovered before the actual find was. They knew that it would exist, and then they finally found it. So how is what you're talking about similar or dissimilar to that example?
Well, we're not doing the crystal structure analysis in that way, but you certainly could. I think to my colleague Peter Burns, for example, working with Frank Hawthorne, and these discoveries of the most amazing new minerals, Ewingite and paddle wheelite and so forth. These incredible. So Peter has used these, consistent data methods, finding lots and lots of uranium minerals and seeing patterns in them, and then being able to predict other sorts of arrangements that probably are out there, and also very quickly recognizing when the new mineral is discovered, as they've discovered so many, that it fits these patterns. So mineralogy is becoming a very data-rich science, and I think that that's the opportunity in the future that my colleagues and I are really pursuing.
Now, would you say that is the largest kind of advancement or change in mineralogy in the last 5 or 10 years, or have there been other things that have been similar to that in the field of mineralogy?
Ryan, there are so many advances. I mean, and I think first and foremost, you have to just say the incredible rate of discovery of new minerals. I mean, around the world, this is something that just blows me away. I mean, just I mean, at the risk of insulting the many people I may not mention, but think about Tony Kampf and Stuart Mills and all the minerals that they've been describing. I mentioned Frank Hawthorne and Peter Burns and the uranium minerals, and Bob Downs and Heshon Yang at Arizona and the Rough Project, and Chi Ma. I mean, this just is incredible. Chi Ma is at Caltech working with often with Alan Rubin, and he uses electron diffraction to find new nanophases in meteorites, and they have discovered incredible stuff: scandium garnet, scandium pyroxene, zirconium phases, titanium 3+ phases, nanophases that who know they existed. And these are some of the most ancient minerals in the cosmos, and they're just being discovered now because of these new techniques. And then, of course, in Russia, I just think about the Kola Peninsula and the things that are being, the Tolbachik fumaroles and the volcanoes in Kamchatka, and Britvin and Filatov and Kravovichev and Pekov, and all, just an amazing group of researchers who are finding these extraordinary new minerals. And the Italian mineralogist Luca Bindi and the things he's doing with the Hatrium basin, these pyrometamorphic minerals, they're just incredible finds that are, and you find new minerals, the Czech Republic and Slovakia and Sweden and South America and of course China, all the things that are coming out of China now and South Africa, and it just goes on and on. I mean, I think those are remarkably important contributions to mineralogy, and so many of them are new structures that no one has ever seen before. But that's one thing. There's also some really exciting stuff going on in the last few years with planetary mineralogy, and particularly a shout out to my colleagues in the Chemin instrument. That's the first X-ray diffractometer on another world. And David Blake and his colleagues, the invention of this Chemin instrument, and the fact that we now have rigorous quantitative information on mineralogy from Mars, and some of the extraordinary discoveries of the abundance of clay minerals, but also the finding that Mars soils are very high percentage, in some cases more than 50% amorphous materials. That's really telling us something. And I think a future mineralogy is to deal more explicitly with amorphous materials, soils, things like that, right, which are so hard to work with, but we need analytical techniques that help us understand them in terms of compositions and the structure. And I will say that I think of the last 10 years, these data-driven approaches and the building of large mineral databases has been fundamentally important and will change mineralogy. The next 10, 20 years in mineralogy, we're going into an era of big data that's going to make a very dramatic difference for a lot of us.
Well, I think that's very exciting. And for some viewers who may be asking the question, well, so what? What difference does it make? What you're talking about really allows us to understand history in a different way. So maybe you can talk about that for a little bit.
Well, it's certainly true that amongst the questions I think mineralogists can be asking in new and more sophisticated ways, some of them have to do with this idea of planetary history and evolution. And indeed, this whole concept that minerals through time on a planet like Earth, they change. The surface mineralogy, the near surface mineralogy goes through an evolutionary process. Now, we've thought about this quite a bit, and as a result, we're introducing, particularly working with my colleague Shauna Morrison, a new evolutionary system of mineralogy. Now, I should explain what that is. Now, I actually sent you a few slides. I know this is a little wonky and lectury, but I want to. It's easier because it's hard to verbalize it without actually showing some pictures. So,
all right, let me pull up the first one here.
If you pull the first one, and I'll just remind people that everything we do in mineralogy, the foundation is the International Mineralogical Association, and the committee is responsible for nomenclature and new minerals and classification. We rely on them. And the 5,700 plus species we have, each one it's a naturally occurring material. It has an idealized end-member composition like SiO2, and it has an idealized crystal structure. And so each species has a unique combination of chemistry and structure. And that's the foundation. That's what we build on. But as you see in the next slide, we're suggesting that these idealized species are not the same as what we would call mineral natural kinds. Okay, let's take a step back. What's natural kind is a concept that goes all the way back to Aristotle, and it means it's basically probing nature, saying, is there in nature something that is a fundamental unit, something that is a naturally occurring fundamental object and represents a true thing? The best example of natural kinds, I think, is the periodic table. In the periodic table, you have atoms classified according to the number of protons, the number of positive charges. And so carbon is 6. And if an atom has 6 protons, it's carbon. And if it's carbon and has 6 protons, and it's not confused with atoms with 5 or 7. And so the periodic table is, by most philosophers' opinions, a table of natural kinds. But in mineralogy, it's a much more complicated problem. And mineral species, as the IMA describes them, are certainly not natural kinds because they're idealized. But we might be able to get closer to this concept of natural kinds by having a complementary system. And that's what we're calling the evolutionary system. And in this case, some IMA species get split because a given mineral like diamond or pyrite can form in many different ways in different environments. Other minerals get lumped together into a single natural kind. And I'll show you an example. And we'd also include some things that are more difficult to include with the IMA system in amorphous materials, non-crystalline. So if you look at the next slide, you'll see I just give an example of pyrite. I mean, pyrite, I love pyrite. Pyrite's it was one of my very favorite minerals, but a recent study we did shows that it forms in more than 20 different environments or ways. And each of those environments is going to have a distinct set of trace and minor elements. It's going to have different morphologies. It's going to have different ages of formation. And so you can think about these as being all pyrite in the IMA sense, but different natural kinds because they represent very different historical events. A biogenic pyrite is very different from a pyrite that forms in a hydrothermal vein. Now, on the next slide, by the same token, sometimes you want to lump things. So there's more than 30 species of tourmalines defined by the IMA. But in many crystals and many individual samples, and blue cap is a great example of that, where you can have multiple species potentially in a single crystal, simply because you have gradations, you have the zoning of different chemical elements. And in these cases, if the tourmaline formed in the same kind of environment, even if the composition shifts so that the Fe to Mg ratio goes from less than 50 to more than 50%, and you officially are changing species, it would be the same natural kind. So that's lumping, and lumping occurs in many groups of minerals, amphiboles and tourmalines and so forth. And on the next slide, I just wanted to underscore this idea that there are really important amorphous materials, volcanic glasses like obsidian. Coal is a natural product, which tells a really important story and is mineralogically extremely interesting. But and James Dwight Dana, by the way, included all of these things in his system back in 1850. But it's more difficult to use the IMA criteria. So we advocate including these. And so in the next slide, you'll sort of see one consequence of this. We can think about the evolution of minerals as a sequence of evolutionary stages, the earliest of which are stellar minerals. And these are minerals that formed even before our solar system and Earth. To me, this is one of the most incredible things that's happening in mineralogy. There's a recent paper that dated an individual silicon carbide crystal at more than 7 billion years old. That's 2.5 billion years older than our solar system. And I was just told by George Harlow, and this may be like confidential, so don't tell anybody, okay? Keep this.
Yeah, go ahead. Tell us on a live program what not to tell anyone.
There is evidence that there may be individual silicon carbide crystals that are 12 billion years old, which is most of the age. The universe is thought to be about 13.8 billion. Our solar system is 4.567 billion by the current dating. And so we're looking now at grains. Now, what you're seeing here is a network diagram, and this is a way we approach this. You say that every mineral, which are these little diamonds that are colored, is linked to one or more kinds of stars in this environment. Because there's different stars. There's exploding stars. There's very energetic old stars called AGB stars. every mineral is linked to one or more of those. And then there's different kinds of stars here, 3 different kinds of stars, and each star is linked to one or more different kind of minerals. This is called a bipartite network diagram, and it shows you how different minerals are linked to different formation environments. So if you look at the next slide, now you can see there's 2 of these presolar grains, as they're called. They're tiny, they're a few microns across, but they are the most ancient objects that we have. As I say, one verified at 7 billion years and maybe even older. So if you go to the next slide, you'll see you can start expanding this. And then as the solar nebula forms, then you start getting new mineral forming, condensing in the solar nebula, and the network diagram accordingly expands. And then the next image, you'll see you can look at the interstellar cloud. And as you look at the next image, you'll see we actually in the interstellar cloud, you have minerals that are not officially IMA because we don't have any specimens in our museum drawers, but these are very, very cold temperature ices that form. And we have various spectroscopic evidence that these crystals are out there. And in the next slide, we can go and look at, now this is virtually all the meteorite minerals, including minerals and things called CAIs and chondrules. And if you have anybody online who's a meteorite collector, something like this, there's a whole bunch of minerals in these objects. Now this object is 4.567 billion years old. It's the oldest thing you can actually hold in your hand, a chondrite meteorite. And it has a set of minerals that formed a long time ago. And then in the next slide, there are additional minerals that form through aqueous alteration and shock alteration and thermal alteration and so forth. So now this becomes a network diagram of all the minerals that are found in meteorites. And I've got one more image to show you, and this is the first time this image has been shown. It's not published yet. It's a sort of prototype, and I want to show you that. And I want to emphasize again that this is work that's been done collaboratively with Anirudh Prabhu at RPI, with Shauna Morrison here at Carnegie. This is a network diagram with 57 different green dots representing 57 different ways that minerals form, and 5,700 blue dots, which are all the different mineral species approved by IMA. And what you're seeing here is a network diagram of all of mineralogy on Earth. Now, there's all kinds of structures in here. And as we start exploring this, there's huge amounts of embedded information. For example, in the very core, at the very center of this diagram, I don't know if can you see my arrow? Is that coming through? Maybe not. But no. Anyway, at the very core of this, you have very ancient minerals, fairly simple minerals. If we colored these blue dots according to how many different chemical elements were in the mineral, so SiO2 would have 2 elements, but there are other minerals that have 10 or 12 elements. You'd find that the core had the very simple chemistry. As you moved outward, you get more and more complex chemistry. The same thing is true for the age of the minerals. The same thing is true for the hardness of the minerals. There's patterns and structures in this that are really fascinating. And we'll be exploring this over the next few years. And this is, I think, one of the futures of applying big data approaches to mineralogy, is being able to see in a single diagram all of mineralogy. We'll be turning this into a wall chart that you can print out and hang on your wall if you want to, with lots of labels and other information. So also, there'll be an interactive online version of this at some point where you can take any of your favorite attributes. If you're interested in optical properties or crystallographic properties, space groups, whatever, you can color this according to that. And you can look for patterns and structure throughout the mineral world. So that's where we're headed.
As we add to the collection of big data, how do you predict this model changing in the future?
Oh, well, obviously, we're going to get more and more information about, for an individual mineral group. Let's take pyrite again. As I said, there's 21 different ways that we know that pyrite forms in nature. If we had a database that, say, had 1 million analyses of pyrite with perhaps 50 different chemical trace and minor elements, maybe 2 or 3 times that many isotopes, morphological information, locality information, age information, you put all that into a data resource, and then you apply something called cluster analysis, which tells you if there are groups of specimens that are very closely related to each other, maybe biologically mediated ones, and other groups that are very different. And that if you go to this, they're all FeS2, they're all pyrite. And so in an IMA sense, every one of those million specimens is well defined. But if you start going to the big data approach, there may be 50 or 100 different clusters that represent different formational and evolutionary environments of the mineral pyrite. And that's really exciting thing to know, because every one of those pyrite crystals, if you have a pyrite crystal, it has a story. This is from Spain. Many of the viewers will have one of these in their collection because they're just fabulous. They're wonderful. But there's a story here. It formed at a time and a place in a certain environment, and that environment and that time and place were different from other pyrites that you may have in your collection. And I love those stories. To me, the ultimate turn on about mineralogy is that it's about vast spans of time, and it's about stories. Now, minerals are profoundly important because they tell us fundamental physics and chemistry, the understanding of space groups, the understanding of bonding and topology, Linus Pauling and the principles of chemical bonding and so forth. These are fundamental things, and that's still really important. And that's not going to go away. Discovering new materials through minerals is not going to go away. The idea that minerals are raw materials for almost everything we do is not going to go away. But being able to see the stories of minerals in this evolutionary context of deep time, 4.567 billion years. That's when the first pyrites formed, by the way. So this is incredible. I mean, we've got an incredible time span, and we've got all these amazing stories to learn, and data science is going to be the way that we learn them.
Fantastic. So what can collectors or people in the mineral world right now do to add to the big data set that you're talking about?
Oh gosh, go out and do what you're doing. Find specimens, add them to the MinDat record. We could not do anything that we're doing right now without MinDat. And that is a resource that has been nurtured not only just by John Ralph and his vision. And what an incredible contribution to the science. But the fact that he's got hundreds, thousands of people that through their own collecting and their own knowledge, and the fact that they become intimately knowledgeable about a particular locality or about a particular kind of mineral, that adds immeasurably to what we're doing. We simply could not do what we're doing without those data resources. And so just keep finding specimens, keep, getting them analyzed, donate them to museums, make these collections open access. And that's what's going to transform the science. It's a group effort. The number of professional mineralogists is relatively small, but the number of people who are passionate about minerals and are contributing to this science is vast. And I just love going to Tucson and just rubbing shoulders with so many people who know so much more about minerals than I do. This is none of us is the only avenue to truth. And everyone you meet knows more about some aspect of the science than you do. So we need to bring that data together, information together, and have this as a shared open access resource that will allow the science to move forward.
Now, it seems to me that a lot of the new finds of minerals are based on deeper analysis of existing minerals. Minerals that we thought were one thing, upon deeper analysis with the better tools that we have, we find out they are actually a little bit different than we originally understood them to be. So if collectors out there have different morphologies or different examples of a mineral specimen, would it make sense for them to have those deeper analyzed?
Well, sure. And analyzing things with new techniques and new approaches is very important. But also, if you listen to sort of the subtext of what I've been describing, this idea of natural kinds, to me, equally important to finding a new species is finding an old species forming in a new way. I mean, I think, one of the great frontiers in mineralogy right now is linking mineralogy to microbiology. And I had the great pleasure of hearing, I didn't know him, unfortunately, but Frank Wright, who was a mineralogist who did microbiology of gold deposits. He worked a lot in Australia. He died much, much too young in 2019. I heard him in just a moving seminar he gave shortly before his death. And he pointed out that some gold deposits are linked intimately to microbes. Now, there are certainly people looking at that and thinking about microbes and mineralogy, but this is a huge world, linking mineralogy to microbiology, linking mineralogy to root systems and soil formation, and different kind of weathering environments, subsea floor environments and ecosystems. It just boggles the mind, the number of things that we could be studying. And I think collectors who go out and see many new environments are ones who can really contribute in this way.
Well, I think that's fascinating that you can take biology and link it to something that seems established and unchangeable like mineralogy. And it makes me think back to the presentation that I referred to in the opening when you talked about the great oxidation event at the Dallas Symposium. Now that kind of blew my mind, and you've been talking about the new mineralogy really becoming a form of storytelling. For the viewers that may be a little bit unfamiliar with it, can you kind of summarize that so that they could see an example of how the storytelling really can change their perspective?
Sure. And you saw some of this just with those network diagrams. So the network diagrams keep growing and getting larger and expanding out. Mm-hmm. And there are these, because each one of those expansions is the result of a new physical or chemical process, or on Earth, ultimately biological process. That's the thing that we find so amazing. So
that's the fascinating thing.
More than 80% of all the minerals on Earth are a consequence of interactions with water. Water is the number one diversification process on Earth. And any planet or moon that is not wet and has an active hydrological cycle is just not going to be as mineralogically diverse as Earth. It can't be. But the second most important factor is life. 50% of all the mineral species that IMA has identified arise directly or indirectly as a consequence of biological activity. Wow. Most importantly, the oxygenation of the atmosphere, photosynthesis, you produce oxygen, and the surface oxidizes, it rusts, and so many of the beautiful colored minerals that we have in our collections. And I love them. I mean, azurite and malachite and all those uranium, yellow and orange and green mineral. They're all minerals that are oxidized as a consequence of biological action. And then there's also hundreds and hundreds of minerals that form directly from biology, teeth and bones and shells. I mean, I'm just fascinated. I mean, this is a fossil shell. The inside is aragonite, the outside's calcite. And the reason it's colored is the calcite is so impermeable to water that the original proteins that are 15 million years old, the shell binding proteins, are still here. If I took this shell and dissolved it in hydrochloric acid, you have these thin plastic sheets of protein that are 15 million years old. And the color comes from the original carotenoid, which is the same thing that colors carrots and many shells today. So, I mean, the fact is the minerals tell us all these stories, but some of the stories are directly linked to life.
That is absolutely amazing. I mean, it really blows my mind. My understanding of minerals was always that, it was a set process that was established at the very beginning of the solar system or the formation of the planet, and it was just a factor of time. But, I mean, it's not a factor of time. It's a factor of time and other influences. Now, you were talking about the effect that water has on mineralization. Going back to our conversation on Mars, we're finding more and more evidence that it once had a bunch of water on the planet. Yep. What do you predict we might find with that perspective?
So, Brian, the big unknown there is to what extent is there an active subsurface hydrological system where hot water is moving around so it can dissolve and then reprecipitate elements. If, for example, there were very large meteorite impacts on Mars early in its history, when there was much more water in the surface before, we think the recent hypothesis is that the water has basically turned into clay minerals, near surface clay minerals. And so most of Mars water is locked into clays, in which case it doesn't have an active hydrological cycle. But if there were active flowing, especially if you had a big impact and you had peripheral fracture zones where hot water circulated and mixed and dissolved and reprecipitated, you might have hydrothermal ore deposits in those peripheral regions. They have not been discovered yet. And I think that that's highly speculative. But if there is that kind of mineral diversity, sulfides and sulfur salts and some more exotic minerals, it'll be because of water circulation earlier in Mars's history, before all these clay minerals locked up the majority of, and other water was, of course, locked into ice or frozen.
Incredible, incredible. So as we're progressing with the probes on Mars, we are continually learning more, and I'm looking forward to what's going to come from that.
Yeah, new minerals are being found at a regular basis. It's a very exciting time.
Fantastic, incredible. All right, we're going to go ahead and launch the poll. So Bob, you're going to have a screen that pops up, or a window that pops up on your screen, and you can go ahead and close that if you want.
I did that, so I will not have a hint as to what your mystery questions are today. I can't wait to find out, though.
I have a question, if you don't mind. I'm going to make myself the devil's advocate here.
Sure.
Uh-oh.
Yeah, because, people think that once everything is entered into a database, we don't need the mineral specimens anymore.
Oh.
What do you think about that?
Oh, that would be the worst mistake because of a couple of reasons. First of all, we love the minerals, right? I mean, I have mineral specimens. You don't want to get rid of the mineral specimens. That's just like, they're great. But more importantly, we're going to have new analytical techniques. We're going to be able to measure things with greater precisions. We're going to be able to measure isotopes that we couldn't measure before. Just think about what they couldn't measure 100 or 200 years ago, and imagine 100 or 200 years from now. And so the museums are critical, and collectors are critical. These specimens, look, you're holding the evidence, you're holding the stories in your hand. That's what you're holding when you see these things. This is not some abstract thing that you can just, let's take a photograph and measure it and then throw it away. No, the stories are, we revere the stories. The stories are.
But that's something we in the museum world, that's something we are really always struggling with. People think, but you just take a 3D picture of your mineral and that's it. It's like, come on, 50 years ago, we could not even measure the structure of minerals based on if the minerals were smaller than 1 millimeter. Because we had to reduce them into powder. But now, 50 years ago, we can now measure the crystal structure of minerals that are 10 micrometers in size. So that's always something we have to convince the people around us, the people driving the museum. Why do you show so many mineral species? Why is it so meaningful? And why don't you only show the beautiful fluorites, the colorful fluorites? So thanks for putting that into perspective. Big data is highly important, but keeping the mineral species, the mineral specimens for future generation is also very important.
Yeah. Well, I think about isotopes. I think about isotopes and the fact that we can now measure dozens of isotopes simultaneously, whereas 20 years ago it was laborious to get one measurement. And who knows? I mean, the idea that so much information is contained. And also, I think many mineral specimens in museums have microbes. Now, some of those microbes are going to have been collected with the minerals. Others are going to be growing on the minerals. Think about the fact that if you have, an arsenic-based specimen or iron, or you may have entirely different microbial cultures on them. And so there may be a future of a new kind of ecology of museums, where we learn things about microbial populations simply because museums are great places to have isolated all these different chemicals that are in drawers and stored there for a century. That gives you an opportunity to do science that maybe no one's ever thought of it. Maybe that sounds like a crazy idea, but I don't think any of us knows 100 years from now what we're going to think are the really important questions. So we need to do that.
Well, Bob, I love it because you are. It seems like you're passionate about big data, but I think what it really distills down to is you're passionate about the stories that can be told. And so to translate it to people questioning museums as to whether or not it is prudent to maintain these vast collections, we have to tap into the stories that these things can tell us as we advance in technology in terms of being able to analyze them. And I think it's the stories that always bind all of us together. It's been that way since even before the Greeks, but it's always the stories that kind of pulls it together and makes us understand why this is important.
Well, we're part of that story.
Yeah.
I mean, we're part of that story in a large sense, but I mean, we have minerals in our bodies, and that's part of the story too. You know, teeth and bones and other mineral concretions. There's so much that we don't know about this mineral world, and you need to have that reference collection. We need to have IMA providing the foundation, and then we need to keep thinking in creative ways about what these minerals are telling us.
Absolutely. Now, Bob, I know we have a ton of questions from the audience, so I want to get to that point. But before I do that, we have to do our quick fire 5. So are you ready for this?
I got my fingers crossed that I'm not going to make some horrible gaffe here, but we'll try. We'll try.
Don't worry. All of your answers are correct. We're just seeing what the audience figured. Okay, quick fire 5 questions for Bob Hazen. Question number 1, James Bond or Sherlock Holmes?
Oh, Sherlock Holmes. Sherlock Holmes.
No hesitation there. Number 2, this is potentially the most important one, beer or wine?
Beer.
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 Number 3, I think this is going to be a tough one. Big data science or storytelling science?
But they're the same thing. They're the same thing, but I'm going to say storytelling because, you know, I at heart, I like stories. But I like big data too, so that's really hard. Very, very difficult.
All right, well, we're going to go with storytelling because I think that's what you would have said anyway. Question number 4. Question number 4. Volleyball or soccer? And when I say soccer, I mean proper football, not
volleyball. You'll see. I don't know if you can see. There's trophies around here. Those are volleyball trophies. They're not soccer trophies. I mean, soccer is a great game, but so is volleyball.
Trumps. Okay. Final question. This is a tough one. You might have to think about this a little bit. Trumpet or saxophone?
I don't have to think about this. Trumpet. Trumpet.
All right. That was our quick fire 5 for Bob Hazen. Eloise, are we ready with the viewers' answers?
Yes, we are.
Okay. Question number 1, James Bond or Sherlock Holmes? Without hesitation, Bob went with Sherlock. What did our audience say?
The audience said the same thing, Sherlock Holmes. Yes.
Nice.
Bob is recognized a bit in Sherlock Holmes, vice versa.
Absolutely. Question number 2, beer or wine? Again, without hesitation, we went with beer.
Beer, indeed. Maybe a beer hour on Friday night at Carnegie, for example.
Shoo. Bob, what's your favorite kind of beer?
Oh my gosh, that's so hard. It's whatever cultural environment I'm in. So Xingha in China and Kingfisher in India and Kirin in Japan and or Sahi. I mean, they're all great. And Bikini Blonde.
Bikini Blonde, okay. I love it. When you come visit us out here, we're going to load you up with longboards.
Longboards, there you go.
All right. Question number 3, big data or storytelling? What did our audience say, Eloise?
It was almost a 50-50, but
okay.
It was 53 big data science.
Okay.
Well, okay.
It was pretty close.
They're not wrong. Don't feel bad. The 53% of you don't feel bad because big data. You've got my mind here, but my heart's the storytelling.
So they're not wrong, but the others were just a little bit more correct.
That's right. Yeah.
All right. Question number 4, volleyball or proper football, aka soccer?
And people answer proper football, unfortunately.
Really?
Yeah,
Okay.
you have to put your trophy next time next to on your background. So
I think so. All right, final question. Trumpet or saxophone? I hope nobody got this wrong.
Sax.
What? I was surprised to see that.
51%, okay? So
it's interesting. Yeah.
We need to
tell us about your the final time that you played trumpet.
Yeah. So for those of you who who don't know me, I almost went into professional music. I studied at the New England Conservatory when I was in university, and played trumpet professionally for more than 40 years. And my last concert was, the last big orchestral concert was the Mahler Resurrection Symphony. So literally going out on a high note. But yeah, so trumpet has been it almost got me, but I realized, and it's pretty obvious to anybody who does this, being a professional musician, you cannot do science on the side, but there are many, many, many very good scientists who have done music on the side. And so I was what's called a freelancer, which means I pick up a job here, pick up a job there, but was not a permanent member of a full-time orchestra, which.
Gotcha. Well, so, I love it because, I'm sorry, go ahead, Raquel.
It's just really along those lines, we have a question by a PhD student who is struggling because he has to stop playing trumpet to dedicate his PhD. So he would like to know what would be your advice for balancing these different interests on a long-term career.
Oh, that is a great question.
So it partly depends on what kind of trumpet. If you play jazz trumpet or big band trumpet or brass band trumpet or orchestral trumpet, but an instrument like that, you really can keep up a level of proficiency. And there are many very, very fine non-professional groups, as well as part-time groups and so forth. So I think I know many, many scientists who had wonderful musical experiences, some cases careers, but often just working, with friends, having your own band, and you play from time to time and so forth. And I just really encourage people to follow your passions. If you love music, don't give up the music, make that a complement. And I think many of the most important scientific ideas I have had, if I've had any important scientific ideas, are because I got away from the science. I got away from the details of the crystallography, the space groups and the unit cell dimensions and so forth. And was talking to musical colleagues. They said, "What do you do?" "Well, I'm a scientist." "Well, what do you do?" And then you have to explain to someone what your scientific passion is, and to make that something that's meaningful to people, you have to talk in their language, not using the big words or all the complex vocabulary. You have to tell them a story. And to me, that has transformed the way I do science. I step back from my science and think about how's this. So merging mineralogy with biology, merging mineralogy with planetary history is just second nature, because that's the story. That's where the story comes from. So please don't give up trumpet if it's your passion, if you love it. Just recognize you can balance that and not spend all your time at it, but you can still find musical outlets.
Wow, incredible answer, Bob. Thank you for that. And I love the fact that you ended your trumpet career on an absolute high, recognizing there was nowhere else that you're going to go above that. And I also appreciate it that this is going to be your last live interview, because you can't get better than Mineral Talks Live.
I'm hanging up my hat. I'm going to go into seclusion. So it's been nice to know all of you, and what more can one say?
Not much.
I'll just click the leave button right now.
Before you go into inclusions, please, we have many more questions. Can you?
Okay. Well, I'll ask a couple more questions before I quit.
Hello, let me go with some of the ones that were on the chat, and then you can also do some of the Q&A, because we have really interesting ones. So going back when you were talking about minerals, someone asked if you could tell us the difference between amorphous and a non-crystalline phase.
Oh. So amorphous to me means something like a natural glass, which strictly does not have a periodic structure at all. But there are all sorts of other phases that are not strictly, that do not have a space group and unit cell, but have elements of crystallinity. I'm thinking about, for example, the mixed layer clay minerals, where every layer is in a different orientation or maybe a different thickness, and so just a random. So it's not amorphous, but it's not crystalline in the sense of a calcite, Elmwood calcite crystal. But it's so much more complicated. I really encourage people to read an article that just came out in Mineralogical magazine by Frank Hawthorne and colleagues, where he introduces the idea of an archetype. And that suggests that there is one extreme where you do have minerals that you can define in terms of a space group, a unit cell, Z, which is the number of formula units, and the idealized chemical formula. You can put those things together. And most minerals fit that description. So what I would say is that there's a large number of other naturally occurring solids that to one extent or another, you can't assign all four of those attributes to, but still they are important. So here's an example of something that's traditionally called limonite and pyrolusite. There's virtually no, if you did an X-ray diffraction pattern of this, you wouldn't get much of anything. So there's manganese and iron oxide hydroxides that are sort of nanocrystalline or poorly crystalline. Nevertheless, they're, that's pretty interesting stuff to study if you're interested in biomineralization. There's a lot going on in this. This specimen, by the way, is probably about 5 to 10 years ago. So you got 5 to 10 years ago versus 4.567 billion. That's mineral evolution for you.
Thank you. So going back to when you were talking about the fossil that you have in there, was the protein making the shell orange when the snail was alive?
Yeah, so this snail was probably, there are some modern living relatives of this thing called the Ecphora. It's the state fossil of Maryland. And yeah, the shell binding proteins had in them coloring agents, carotenoids. And that would have made this. And you do find some of these shells, if they're very, very well preserved, they're almost an orange-brown color, really quite spectacular. And interesting thing is, if you leave this in the sun, it will fade to a very pale brown. So there is some decay, photooxidation or decay in sunlight. But when you first collect them, they can be quite colorful.
Yeah. And another one, is there a way to use the type of minerals from Mars to biological activity?
That's one of the biggest questions that we try to address or think about. Is there any mineralogical biosignature? And there's different possible answers. It's conceivable that there are a few mineral species that if you found that species, you could say, that's a probable sign of life. Or maybe it's an assemblage of minerals that's a probable sign of life. More subtly, we think that, that network diagram that I showed you earlier, we think that the structure, the interconnectivity of that diagram may itself be a biosignature. That if you look at a similar network for Mars or for the moon, there are aspects of the structure that are very different from this. Now, that's something it's purely speculation, a hypothesis right now, that we think that there may be underlying structures in the occurrence and co-occurrence of minerals that suggests at a planetary scale whether or not there's been the influence of a biological system. So that's a hypothesis. And so we're going to look into that. It's a lot of fun. These are the kinds of speculations you can start make when you have big data to work with.
So along those lines, where do you see trinitite?
Trinitite. Okay, trinitite, if I'm not mistaken, is a fused rock type that's associated with the atomic bomb experiments. So in a mineral evolution context, that would be considered an anthropogenic mineral or rock type. I don't know whether it's a single phase. If it's a single amorphous phase, then we would treat it as a natural kind that was formed through anthropogenic processes. But that would need more research. That's actually the kind of question that we're extremely interested in. Hey, I've got a question for everybody else. I'm sorry, it has to work both ways. So I showed you that picture earlier of the quartz crystals that had alternate faces. And then when I was at Tucson 2 years ago, I found this specimen. Now this looks like it's probably some kind of chalcedony with some kind of carbonate, probably calcite, but look at the alternate coatings. So my question, there was no label with this specimen, but I bought it. I bargained them down to at least a semi-reasonable price. Does anybody out there know what this is, where it's from?
It's from India, Bob.
India?
Yep.
Somebody who knows that?
From the Deccan Traps.
That's from the Deccan Traps. Oh my goodness. And what is the black coating on alternate parts of the
Come on,
carbonate?
Alan. Come on, Alan. We are waiting for you.
Wow, you see, this is what I mean. No matter where I go, no matter who I meet in the mineral world, they always know things that I don't know. And this is why we can learn so much from each other. This is why having this rich collecting community is vital. So I want to be able to put a good label on this. So when I donate this specimen to Harvard, you'll know where it comes from and what it is. I mean, that's really important.
Alan, do you have
Alan Hart is saying that he bought one and it's from India. So maybe, Alan, if you have any additional information that you can share.
That'd be fantastic. See this, I love this community.
Alan, open your mic. Open your mic.
Our collective knowledge is so vast. That's why we need to have this large data resources that brings it all together so that we all just have fingertip access to this kind of knowledge. Alan, thank you.
Hey, hello. That's a great talk, Bob. Good to see you.
Hey, Alan, thanks so much.
Yeah, no. But I saw two of these specimens in Tucson about 3 years ago, and I tried to nab one, but it was purchased off us out the blue, the big one. But there was a smaller one because there's some preferential growth, like your first slide with the quartz, yeah?
Yeah.
On 10 bar 11, we think, because it's a Cumberland habit, but it's been extended.
Oh,
it's really interesting. I think they're graphitic inclusions, but I think Mike Rumsey was going to put it under the electron microscope back at the museum and see what it really was, but it's really strange.
Interesting. It sort of looks like a sulfide to me, but I don't think it's I don't know. But
no, yeah, I didn't actually I left it at the museum, didn't have a look at it, but it's really interesting preferential growth on those faces.
It is.
But, you know, one of the things was also pointed out is you've got to be careful with these things because some unscrupulous dealers might just take off the other things just to make it look nicer.
Right. Absolutely. I'm completely with you there. So I think mineral surface science is one of the exciting directions for the future, by the way. I think there's so much we can learn about surfaces, how they interact with the environment, how they might have played a role in the origin of life. Wow. We've just scratched the surface of mineralogy. There's so much more to learn.
Totally. I totally agree. Brilliant, man.
Excellent. Thank you, Alan.
Cheers, guys.
Yes. Elo, do you want to go ahead with some of the many questions we have? We share duty today.
I'm sorry. I was texting Mike to see if you had the answer. Can you just go for one more question?
Yeah, from Brian, he's curious how mineralogists will or not include man-made crystals in the evolutionary system.
At this point, we're not including human-made crystals. We contributed a paper a few years ago on mineralogy of the Anthropocene. Now, Anthropocene is the name that some geologists are giving to the modern era where humans really have a significant impact on the surface environment. And we listed what we considered to be a few hundred minerals that certainly formed by human processes, slag minerals or mine dump minerals, mine tunnel walls, things that occur in coal mine fires and so forth. But we do not include synthetic phases per se, although any classification system can be modified and expanded in whatever way we want to. So in the future, we may decide that this is really important, particularly for phases like, say, silicon wafers in electronics or phosphors or battery materials and so forth, where they may have a long-term life. Laser crystals. These things may survive a very long time in a geological environment, in which case we might want to have some kind of catalog of what they are. It is intriguing to me that as I understand the rules, if you have a electronic, say with silicon crystals, that those silicon crystals are not considered minerals, but if you have a natural weathering process of some human artifacts, they are considered minerals. And so there's all these gray areas. It's just a matter of us as a community deciding what we want to include and tabulate. That's because classification is a human endeavor. It's not necessarily intrinsic to nature, but but it's what we think it should be.
How does scale and time influence mineral diversity? Are there minerals with isotopes that have short lifespans?
This is something we've speculated on, the idea that there might be, for example, plutonium minerals that form very, very early. Plutonium is so PuO2 could have been a mineral phase very early in the cosmos, perhaps a phase that formed in meteorites, but then the plutonium would have decayed. And there's some other examples there's similar sorts of things, minerals that have gone extinct through various processes that may very well have been abundant at one point in Earth history, but no longer are. One of the obvious ways that that could happen is if you had extreme cold periods, so that CO2 would freeze. And so crystalline carbon dioxide could have been a phase on Earth at some point in some very, very cold regions, the Arctic, for example, but no longer because the temperatures are too warm for that, and they could come back. Ice could be a mineral that goes extinct on Earth if we have significant warming.
One by Steve Malansky. Could you discuss the problem about mercury mineral diversity?
Is that mineral diversity on the planet Mercury? Is that what it said? Mercury mineral diversity?
Yes.
I'm not as much of an expert on Mercury, but since it does not have any obvious hydrological cycle, we know that that severely limits things. However, it does have some volatile chemistry, which I think is intriguing. I understand that there are evidence for sodium and sulfur vapor, or indications that there may have been a more active sulfur cycle. So there may be some interesting mineral anomalies. I know there's thought to be very reduced sulfur phases like calcium sulfide. So what is that, oldhamite? I've got to dredge that up from my memory, but some phases that are not common on Earth, or that may be only known from reduced environments in meteorites, would also be common on Mercury in that case.
Are we close to understanding the mechanism for how life was triggered, from non-living chemicals to life?
Well, it depends largely on who you talk to. There are many researchers in the origin of life. We're certainly closer to understanding some of the principles involved, that it's a process of chemical complexification. And one of our hypotheses is that mineral evolution, which shows this increasing diversity and complexification of the chemistries of minerals, adding more and more elements is essential to certain mineral species, for example, very much parallels the kinds of chemical complexity that must have led to the origin of life. That's organic chemical complexity. The idea of it being triggered, the idea of it being a sequence of deterministic or inevitable steps. Maybe some people think there's just a chance juxtaposition of molecules that led to it, so that it's not so common in the universe. These are huge debates in the origin of life community. And until we find a second genesis, a second origin of life, if you go to Mars, for example, and find a different kind of life, until we do that, then everything becomes really speculative about whether we are alone in the universe, or whether the universe is just filled with living planets of different kinds. Really important questions. They're things that we can study experimentally to some extent, but largely these questions remain philosophical until we have more tangible observational evidence.
We have another one by Stefan from the Yale Museum. So every year up to more than 100 new mineral specimens are described. Is there an estimate of how many more than the currently approved 5,703 species are still to be discovered? The way he's asking more about minerals according to the current definition, which I'm not so sure what he means by that.
Yes, and that's a very important question that we tried to address with a spin-off of big data mineralogy called mineral ecology. Mineral ecology is the systematic statistical study of the diversity and distribution of minerals on Earth today. What we find is that the vast majority of mineral species are rare. More than half of all known mineral species are only known from 5 or fewer localities. In fact, something like 1,500 mineral species are only known from a single locality. And so you can do the same kind of statistical tests of minerals that ecologists do when they go into a forest and they look at birds or they look at insects or trees, and they say, we measure 1,000 trees, and each time we see a new tree, there's a reduced chance of finding a new species. But you haven't found everything. And so they have what's called an accumulation curve that sort of looks like this. It's leveling off. And you can do the mathematics, which we've worked with our mathematician colleague, Greta Heisted, who's now at Purdue. And she has shown that they're based on current discovery methods, assuming we're not going to find some whole new way of finding new minerals, that there may be between 9,500 and 10,000 species using the IMA definition of species. Now, we're going to try to do the same thing with our estimates of natural kinds, which may run up closer to 20,000. But because that assigns also paragenetic modes, the way minerals form. So there may be 25 different kinds of pyrite in that case. But let's just say that there's still a lot of things to be discovered. And as we add new techniques, if more and more people have electron microscopes and can do what Chima does on more and more different kinds of samples, it's conceivable. And if we want to define minerals as being, anything that's 5 nanometers or larger, there may be all kinds of mineral phases that have yet not even been tackled, that no one's really been looking for yet. So, but there's thousands of specimens to be found. But I think that today's crop of mineralogists are doing an amazing job of identifying new species. Very inspiring.
That's a very big number. It's almost like, wow.
Well, not quite double what we have now.
Yeah, but incredible. Another question from Tony Albini, and it's regarding the oxidation event. His understanding is that stromatolites, sometimes called pond scum, pump huge amounts of oxygen into the atmosphere and had a huge effect on our planet. Do you see any other significant changes occurring at the present time?
So the question is, are there atmospheric changes that are going to change mineralogy? Of course, there are big atmospheric changes from a climate perspective. And I think that if there are big mineralogical changes, it's going to be likely because a warmer, wetter planet accelerates weathering processes, soil formation, and of course, you could eliminate, as I mentioned before, ice as a mineral that could go extinct for a while. But I don't see the same kind of what in evolutionary terms we call a punctuation event. The thousands of new minerals that form because of atmospheric oxidation and the near surface oxygenation of the planet. That really was what may be irreversible, but it was a very large event, starting probably beginning around 3 billion years, but really taking almost 1.5 billion years for the oxygen levels to rise high enough that it was pervasive in the near surface environment.
Another question by Stefan. What was the feedback to calling the increased mineral complexity on Earth evolution?
Well, okay. Right. So we did that with a little bit of recognition that biologists thought that they owned the word evolution and that no one else should use it. And so we got some real pushback. Minerals don't evolve, calcite crystals don't evolve. That's just a calcite crystal. It's always going to, and yet the word evolution has been used for more than a century. Norman Bowen talked about the evolution of the igneous rocks. We talk about the evolution of meteorites. We talk about the evolution of planets. And evolution means change through time. That's the most basic definition. And so in that sense, the planetary mineralogy has changed through time. It also tends to mean complexification, that is, you go from less diverse to more diverse and more complex. And we see that not only just more diverse, but much more chemically complex mineralogy. The complex pegmatites don't show up in the geological record until about 2.5 billion years ago, for example. Agpietic rocks and the incredible mineralogical complexity of those are even younger, so that there is that complexification. There's also something in evolution called congruency, which means that each stage of evolution follows from the one that came before it. It's not just a random bunch of events. And in those examples, mineralogy fulfills the definitions of any complex evolving system. It's not Darwinian evolution. It's not natural selection. There's different selection mechanisms, but there is a selection mechanism, and it has to do with how water and rocks interact and how life also selects elements and concentrates them, and that's how you get new minerals. These are great questions.
I guess you see them. From Ivan, what's your favorite fluorescent mineral and favorite phosphorescent mineral?
Oh, well, I mean, I go back to Franklin, and I wish I could show you this one's fluorescing and phosphorescing, but the reds and greens. And I have to say, George Harlow gave my wife Margie and me a little tour of the new exhibit at American Museum of Natural History that opens on June 12th. And one of the most jaw-droppingly spectacular things I've ever seen in a museum is their 10 by 20 foot slab of polished Franklin material. And they have several different wavelengths of light, and it goes through, and then they let you see the fluorescence in long wave and short wave UV, and then they let you see the persistent luminescence of the willemite and some other minerals, and then you get to see what the slab looks like in natural light. And it's just, if you can get to New York after June 12th and get to the American Museum, that exhibit is just truly jaw-dropping spectacular. And you'll see two of my favorite fluorescent minerals there.
Yeah, I think we are there. Brian, Eloise, any other questions?
Thank you very much, Bob. We had so many questions, a lot of great comments. People read a lot of your articles and books and things who were interested. So it's a lot of comments. I know that Raquel will save the chat log. So if you want to look into this later, so many good comments. Thank you so much for being with us directly from Carnegie.
Well, thanks so much to everyone for tuning in. It's such a pleasure to be able to talk with my colleagues in mineralogy.
Well, Bob, really appreciate you coming on. I'm fascinated. I keep glancing off to the side because this is where my chat window is, and I'm fascinated by the conversations and the questions that have been going there. So definitely we'll take a copy of that chat window and send it to you, Bob. Really appreciate the time that you've spent in answering all the wonderful questions, also wonderful answers. So thank you so much.
Oh, totally my pleasure. Totally my pleasure.
Right on.
Best
So for all you viewers out there, tune into Blue Cap Productions YouTube channel tomorrow, and we are going to be releasing our interview that we did with Barbara Barrett and Dr. Carl Francis from the Maine Mineral and Gem Museum. That was originally aired on May 5th, and absolutely wonderful episode. A lot of fun shooting that, and that will be released tomorrow. Now, before I announce next week's guest, I have a small announcement to make. Speaking for the entire Mineral Talks Live crew, next week's show has a very special meaning for all of us. In fact, it's actually kind of a double meaning. To begin with, next week's show will mark the 1-year anniversary from when we first started broadcasting Mineral Talks Live. That was back in June 3rd, 2020, when our very own Eloise Gaillou took us through her museum, the Paris School of Mines. At the time, little did we know what we were starting, but wow, what an incredible ride. We want to thank all you viewers for tuning in week after week. Second special meaning for us is that next week's show also will be our 50th episode, and I can't believe we've already done 50 episodes. As everybody knows, the 50th anniversary celebration of anything is celebrated with gold. So we couldn't think of a better guest to have on our show next week than Mr. and Mrs. Gold themselves, Donna and Wayne Light from Crystalline, Laguna Beach, California. And to top it all off, this year also happens to be their celebration of 50 years being in the business. So make sure you tune in next week for our solid gold episode of Mineral Talks Live with Donna and Wayne Light. For all of you out there, we hope that you have a wonderful and safe Memorial Day weekend. Welcome the summer in. Mahalo for tuning in. We'll see you next week. Take care.